Okay, in this video we want to look at something called interference. Our first little animation we're going to look at here is right here, constructive interference. I'm going to blow it up here a little bit. And you'll see what just happened there. We had two waves coming at each other. And what happens when they hit each other? They actually build or construct up on each other. And I could ask you, do you think they bounced off each other, or do you think they went through? And that'd be kind of a tricky question. It'd be hard to kind of really tell, but the answer is that they actually do go through each other. Waves can exist in the same spot at the same time, and they can just travel right through each other, because really all it is just energy. But this is constructive interference. So you might have two waves here, and they have an amplitude of like maybe this is 2 and this has an amplitude of 2. When they keep going towards each other like this, they're going to actually build, and they're going to construct a larger wave, and it's going to have an amplitude of 4. So this is a really easy problem on your Jedi trial, is that constructive interference, they just add together. Now, if you had a wave that was like an amplitude of 2 and there was an amplitude of 3 and they were going at each other, when they hit, they actually would make an amplitude of 5, and then the 2 would continue going on this way and 3 would continue going on this way. So this is just constructive interference, and you just add the two waves together. It would actually be like twice as loud. If this is a sound wave, it would be twice as loud at that particular place. Okay, let's look at destructive interference. Same kind of thing. We have two waves coming in here, and they would cancel each other out completely, and then you can see that they just continued on through. These have the exact same amplitude, so when they hit each other, this is total destructive interference. One of them have an amplitude of +2, the other would have an amplitude of -2, and together they have an amplitude of 0. Let's see if I can freeze it right at the right. Ooh, thought I could maybe do it right there at the right moment. It'd be kind of a fun little skill. Hey, that's what you should try to do. Try to screenshot it so that you see nothing but a straight line. It's very difficult to do on here, so maybe you can get it to happen. Okay. So again, on this, if I had an amplitude of something coming in had an amplitude of 5, and then here was an amplitude of 2, or basically -2, what they would join together would be an amplitude of 3. It'd be upward displacement of an amplitude of 3. So destructive interference, you're subtracting the two amplitudes out. I think that's probably pretty simple and straightforward. Okay. Let's go to something really unique. We're going to talk about interference patterns. So if we have two point sources, for instance, like we have a water fountain here, and I can turn it on, it's going to start dripping drops. And this part is easy to understand. It's going to make concentric circular waves that are traveling outwards. That's not a problem at all. That's easy for everyone to understand. Now the problem is if we turn on another dripper. This is going to make concentric circular waves also, but as those concentric circular waves travel outwards, they're going to start interfering with the waves that are coming from the other one, and we get what's called an interference pattern. Now, interference patterns are a little more difficult, it seems like, for students to understand. All we did was turn on one more dripper, and now it's really difficult to get what's going on. But we have an interference pattern here, and I'm going to go ahead and freeze that. And what you'll see here is a whole bunch of, I'm going to turn this to be like yellow, I think. If you look, you'll see these blurry lines. See those blurry lines? Here's another one right here, right? Okay, and there's another one starting back in there, and There's one in there, and there's one there. There's one there, and there's one right there. Those are blurry lines. Those are called nodal lines. Nodal, N-O-D-A-L, nodal lines. And the reason they're nodal lines is because basically one crest from one of the drippers and one trough from the other dripper have met up, and they have completely canceled each other out because the amplitude of these waves are the same. So one of them is the amplitude's down, the other one the amplitude's up, and along these nodal lines here, there's complete cancellation of the waves. There's no energy there. In fact, if I was swimming, if I was like swimming across in front of these two drippers out here, there'd be places right here and here and here and here where I would just be in pretty much still water. The water would be completely still. Now on either side of me, it would be going up and way down, because in between these places, we have places of constructive interference. So the nodal lines was destructive interference, all those blurry lines. But in between here, we have this really big crest and a really big, here's another really big crest and a really big crest and a really big crest. But in these black regions in between there, they're really big troughs. Okay, so what's happening is a crest from one wave is meeting a crest from the other dripper, and they're making a really big wave, or they're making a really big trough. So these areas in here are called anti-nodal regions, okay, or anti-nodal lines through here. So I'd have an anti-nodal line here, and here I have another one that's going through here. Okay, and here's another one, and here's another one here, and another one here, right? Okay, and so if I was, out here swimming across again, and I was right here at this place, I'd be on a nodal line. I wouldn't be moving at all. But right here next to me, I would see waves going way up, and I'd see waves going way down, right here. This is a big trough. Here's a big crest, okay? Or here's a big crest, and here's a big trough. So I'd see waves going way up and down on either side of me, okay? So I'm going to explain that here in a little bit more. We'll talk about that more again. You should be able to label the nodal lines and the anti-nodal lines and explain kind of what's happening there, but we'll talk a little bit more about that in a second. One thing I want us to notice here is how could I increase or decrease the interference pattern? How could I increase or decrease the interference pattern? Well, one thing I think is probably a little bit obvious is just the frequency of me dripping these things. Right now I have the frequency pegged out, so that's a pretty impressive interference pattern. But what if I lower the frequency down and we kind of wait for it a little bit? Watch what happens to the nodal lines, or how many nodal lines I now have. Okay, so if I freeze that, you'll now see that we have, remember my nodal lines were yellow, so I'll do that. I just have a nodal line here and a nodal line here. Maybe there's another one starting here and another one starting out here. But see, I have a lot less nodal lines, and the anti-nodal lines are these regions, right in here. So I decrease the frequency, I decrease the interference pattern. You make the frequency go really, up a lot, and you're going to have a much bigger interference pattern. So that's one way you can do it. Okay, you can increase the frequency or decrease the wavelength. Either way you want to look at it, increase the frequency or decrease the wavelength, and you're going to have a much bigger interference pattern. The other way to do it is to the distance between these two drippers. Right now they're as far apart as possible. I'm going to go ahead and increase the frequency again so we see our really, really big interference pattern here. Wait for it, wait for it, wait for it. There it is. Look at that interference pattern, okay? But a way to reduce this also is to actually just reduce the distance between the two drippers. I guess it made it start over again. Okay, so if I reduce the distance between the two drippers and I get my interference pattern, you can clearly see here that the nodal line, there's just a nodal line there and there's a nodal line there. right? And then there's an antinodal line regions right in here and in here and in here. So by lowering the distance between these two drippers, we really decreased the frequency pattern. So how do you increase the frequency pattern? Two ways, and either of these will be on your test. How do you increase the frequency pattern between two drippers? You either increase the frequency, right? I mean, how do you increase the interference pattern? You increase the frequency, or you decrease, you increase the frequency, or you increase the distance between the two drippers. That's how you increase the interference pattern. Increase the frequency or increase the distance between the two drippers. All right, so I think I have an animation here somewhere of that happening. Yeah, okay, so here's frequency interference pattern. So here's an interference pattern, and it shows what happens if we increase the frequency, or actually, here's decreasing the frequency. Okay, what we're doing is increasing the wavelength. See the wavelength's going up. So if the wavelength is going up, that means our frequency is going down. So if we decrease the frequency, you're going to see we have less and less interference pattern. You can really see it when right there. Look at all those nodal lines, and now as we're decreasing the frequency, look at there's less and less and less nodal lines in the region. Okay. Okay, you can click on these on the website yourself if you'd like. The other thing is the spacing between the two drippers. So what happens here? So here we have, you'll notice these two drippers, they're getting closer and closer and closer and closer together, right? The slit width is getting less. So what happens in the interference pattern when they get closer and closer and closer together? Again, the interference pattern decreases. Look at how the nodal lines are just kind of going away, and now it's like just basically one, right? So there's a whole bunch of nodal lines here, but they're all going away as these two drippers get closer and closer together. Okay, so if you want to increase the interference pattern, you increase the frequency of the drippers, or you increase the distance between the two drippers. Those are the two ways to increase the interference pattern. Okay, I want to go back to this. I want to make sure we have a good understanding of this. I'm going to make the separation really far apart. I'm going to have a big frequency so I can get the biggest interference pattern I possibly can get. And I'm going to be freezing this and trying to help us kind of understand a couple things. So the question is, why do we have multiple nodal lines? You know, why not just one or so? So I'm going to put in my nodal lines again. So I have a nodal line that goes along here, a nodal line that goes along here, okay, nodal line that goes along here. You know what? I think I'm going to do this a little differently. I'm going to erase those lines here. Let's do this. Let's just look at the interference pattern. Let's draw in the waves. So I have a wave there going around that one. I have a wave, going around there. I have a wave going around there. A wave going around there. There's a wave going around there. So all these waves are coming from this one here. Okay, does that make sense? Okay. So now what about the ones coming here? So I have a wave here. I got a wave there. I got a wave there. I got a wave there. Got a wave there. And we got one that's going to come out. Like this, I guess. Okay, so so we can see how these waves are interfering here. Right down the middle between them, we have crest and crest hitting, right? Crest and crest hitting, and of course we also do have in between here, troughs and troughs hitting also. Okay, so that's an antinodal line right there. Okay, and if you count waves. So like how this point right here, how many wavelengths is it from where this started? Well, there's one wave, two waves, three waves, right? How far is it from this one over here? One wave, two waves, three waves. So these antinodal, this antinodal line across down the middle here is the same wavelength distance between each of these. So this we'll call this a nodal, or an antinodal line, an antinodal line. And this is what we call n equals 0. So and that's basically 0 wavelengths, lambda, 0 wavelengths. And that's the path difference between. So if I take any one of these points, I take this point here, and I measure the path from here out to there, or I measure the path from this one out to there, and I subtract the path difference, I would get 0 wavelength, 0 lambda, because it's like from here, so it's 1, 2, 3, 4, 5 to there, and then 1, 2, 3, 4, 5 to there. So 5 wavelength minus 5 wavelength is 0. Okay, but there's other places, like right here we have crest and crest, crest and crest, crest and crest, crest and crest. So here we have another antinodal line, Okay, so what's the path difference between those? So like let's take this point right here. Okay, how many wavelengths is this point from this wave right up here on the top? Well, 1, 2, 3, 4, 5 wavelengths. Okay, how far is this one from this one over here? 1, 2, 3, 4, 5, 6. So this is 6 wavelengths away from here, but it's only 5 away from this one, and the difference is at n equals 1 lambda. Okay, so that's why we have another antinodal line over here, because it's 1 wavelength ahead, 1 wavelength farther from this one than it is from this top one here. Okay, likewise over here we have the same thing, right? So we have the same thing right here. We have an antinodal line that goes this way. This is another n equals 1 lambda. But this is 1 wavelength farther from this one than it is from this one down here. Okay. And we could keep going. We could have an n equals 2, on further out here a little bit. Okay. All right. Now in the middle, remember, we have nodal lines, right? We have these blurry nodal lines coming here where crests, basically a crest right here is hitting a trough, right? And a crest right here is hitting a trough, and so on. Okay. So if I take a point here, like let's see, like right here, I guess I have a crest. There's a crest right there, hitting this trough right there. Okay, so if I have this crest right here, it's 1, 2, 3, 4 crests, 4 lambdas away from this, right? But it's interfering right here, and so what is that? That's like 1, 2, 1, 2, 3, 4 and a half, right? It's 4 and a half. Okay, so the difference here is that we have 1, 2, 3, 4, I guess. So that's 4 away, 1, 2, 3, 4 away from that, and 1, 2, 3, 4 and a half away from that. So what's the n? The n is actually half of a wavelength. Okay, this n right here would also be half of a wavelength. We could have another nodal line, out here somewhere, right? And this would be n equals 1.5 wavelengths. So your nodal lines are half wavelength distance, path differences between those 2 points, and your antinodal lines are full wavelength differences between them. Hopefully that makes sense. I'm going to have another video, I think, that's going to try to have somebody else kind of show you that and see if that makes a little bit more sense to you. But I hopefully that will, you have a little bit more understanding about interference.